Hi everyone. Today we have our very own Mingkuan as our speaker. Yeah, can you close that window?
My mouse is not on this screen. Oh, I see.
Take your time. Okay, I'll just restart. Hi everyone. Today we have our very own Mingkuan as our speaker. He is co-advised by Zhihao and Umut. Today he's going to talk about his work, Quartz, superoptimization of quantum circuits. Let's welcome him.
Okay, thank you. Yeah, so first, today I'm going to introduce some quantum background and some quantum circuit optimization example, and then discuss the optimization, the design, and evaluation of the work and some future work. So first, for quantum computing, each quantum gate of q qubits is equivalent to a 2 to the q by 2 to the q unitary matrix. And there are some gates contain parameters, and parameters are all real numbers. For example, so the figure on the left is an example of a circuit containing Harman gate, CNOT gate, and U1 and U2 gates. And U1 and U2 contain parameters. And their matrix representation are shown on the right.
So what is the H gate?
Oh, H is a Harman gate, so it's another single qubit gate. And a quantum state of q qubits is equivalent to a complex vector of size 2 to the q. And actually, so the square of the modulus of each entry in the state denotes the probability if you measure the state at the end. And so how to do quantum computation? You just apply the gates to the state. So for example, if you apply U1 theta at qubit 0, it's equivalent to multiply the matrix to the state vector. And notice that so if the system contains 2 qubits, but you are only applying the gate to one of the qubits, it's equivalent to tensor product with an identity matrix, so that you can apply a 4x4 matrix to the vector which has size 4. And note that the unitary matrix preserves the sum of the square of the moduli. So it makes sense for the square of the modulus to represent the probability, because the sum of the square is always 1. And in this example, for example, the quantum state is originally x, and after you apply this U1 gate, it becomes x prime. So it's equal to, so the state x prime is equal to U1 theta tensor product identity times x. So it's like, so write it with a 4x4 matrix. It's like this. And so if we concatenate many quantum gates or quantum circuits, it's equivalent to matrix multiplication. And if we parallelize some quantum circuits, equivalent to tensor product of matrices. So a quantum circuit is also equivalent to a unitary matrix. For example, here we have a U1HH at the beginning. So when doing quantum computation, so it's equivalent to multiplying the U1 tensor product H. Tensor product H. You can also make this. Never mind. So the term on the right, because so the multiplication. So this is the nearest to the vector. So if you put a x on the right of these matrices, and then after you multiply the U1H tensor product H tensor product H, you can go to the second column, which is U2 and the C0. So that symbol is the C0 gate. It's a 2 qubit gate. And so it's equal to multiply a U2 tensor product C0 in the middle. And finally, you have only a C0 in the third column. So you just tensor product, you just multiply it by C0 tensor product identity on the third qubit. And so in quantum computing nowadays, there are, because this is a very new area, so different companies make different devices and they use different gate sets. For example, the IBM, their quantum machine use U1, U2, U3, and C0, these 4 gates. And there are some other frameworks. For example, Rigetti, they use Rx, which is rotating around the x-axis by a multiple of pi over 2, or RZ, so rotating along the z-axis with any angle, and the CZ gate, which is another 2-qubit gate. And NAM and Volk, so there are 2 recent papers. So they use another gate set, which is HX, RZ, and C0. And actually, all of these gate sets are universal. That is, so take any unitary matrix, you are able to represent the unitary matrix in this gate set.
Sorry, what is the X gate?
Oh, X gate is so rotation by pi along the x-axis. So
it's like you flip from 0 to 1.
Ah,
oh yes, yes.
I see.
Or it's easy, I guess. It's like control Z.
Control Z, yes.
Control the first qubit to place Z in the second.
Yes.
What's an upper bound on the number of such gates needed for implementing matrix for like all these gate sets?
So yeah, so for example, so you want to ask, so given a unitary matrix, so how many gates? Actually, it determines it's determined by so how precise you want. So the more gates you use, the smaller error it is. So
Yeah, because I guess you have like real entries, right? So you need to approximate them.
But the parameters are also real, right? So
yeah, so in some cases you can approximate a constant number. So for any unitary matrix, but in some cases, so there's some algorithm that the more gates you use, the closer you approach it.
So even with real parameters, you can't exactly get
Yes, yeah, that's another line for it. Yeah, so how to make it so you use fewer gates to approximate any matrix. But so if given case is very well structured, so for example, you are given a U2 gate and you want to represent in another gate set. So these are already well studied. So they are just constant number of gates. Okay, so talking about quantum circuit optimization is like minimizing the cost of executing a quantum circuit. And there are a lot of different metrics about it. For example, the number of gates or the depth of circuit and the fidelity of the result. So fidelity is like error rate or something, because nowadays quantum computing has some errors. And actually the depth of circuit is the running time, but it's hard to optimize that. So we pick the number of gates which is consistent with some previous papers. So a lot of previous papers use the number of gates as the metric. And how to optimize is like, so apply circuit transformations. That is, replace one circuit with an equivalent circuit. That is a circuit with the same matrix. So because the computation is decided by the unitary matrix. So if two circuits have the same matrix, they exactly the same.
You mentioned depth is hard. Is it harder than gates, or is gates not hard?
Depth is harder than gates because so usually sometimes you cannot do anything on the critical path. So if you optimize along the depth of the circuit, you might find that if you do this transformation, then nothing changes. This is just a guess, but so the main reason is a lot of previous papers use the number of gates as a metric. So to be considered and comparable. And actually, yeah, we can also try to use depth as a cost, but we haven't done the experiment yet.
I asked because in circuit complexity for classical circuits, so the approximation of optimal depth is studied. So is the approximation of optimal depth studied for quantum circuits?
Well,
For example, if you have this classical circuit of logical gates, the problem of minimizing the depth of that circuit.
oh yeah, you mean for example the AC complexity class or something.
Yeah.
Oh yeah, the quantum case is definitely not as well studied as the traditional cases.
So will you increase the depth when you do the circuit transformation?
I don't know.
You don't know if that is possible. Or
Well, yeah, it's possible, but I think it's unlikely. So yeah.
because if you if you do not increase the circuit depth but only reduce the number of gates, then this will be much better than only reduce the number of gates but increase the depth of the circuit very low.
I think in most cases, so they are positively correlated. So
Yeah.
Oh, so here only focus on like applying transformations that exactly preserve the matrix, not looking at the constant.
right. So
So it's possible there's like a very complicated circuit, but like getting a matrix that's like very close to the matrix of Q is like actually very easy. Like,
yes, that's a yeah. I think the program optimization that don't preserve exactly what the program does, which is a very open area. So there's a lot of things to do there. Okay, so maybe let's look at an optimization example. Yeah, so this is so if there are 4 hardware gates around a CNOT gate, then this is equivalent to flip the control qubit and the target qubit of the CNOT gate. And yeah, so for example, we don't know the transformation on the left, and now we have 2 pairs of equivalences on the right. And we can see that we can transform the circuit 1 to circuit 2 here. So it is flipping the CNOT and moving the 2 hallmark gates from the left to the right. And then apply the transformation on the bottom right, which is cancel out 2 adjacent hallmark gates. So we get it. And so previous work, they manually designed circuit transformations, which requires quantum expert to redesign for each gate set. And because there are a lot of gate sets, and yeah, you cannot design some universal ones. And they use some heuristics to optimize. For example, they just greedily transform the circuit towards fewer gates. For example, cancel out hallmark gates, adjacent hallmark gates. And our idea is we want to automatically generate circuit transformations. And know that, so if each circuit transformation that means, what does it mean? So it means that 2 circuits are equivalent. So we can actually save it in a more compact way. So we use a equivalent circuit class to represent a class of equivalent circuits. And for example, here we can say that so this transformation is subsumed in the 2 ECCs on the right. Yeah. So know that so we can subsume this transformation if you only search for circuits with no more than 3 gates, because these two ECCs, they only contain circuits of no more than 3 gates. But this transformation already there's 5 gates in it. So yeah, we found that so we can scale better. So yeah, by
Sorry,
yeah.
I understand. Like you're saying that you can like, so there you're using 5 gates, but you're saying that you can basically just use 3. So like, what's the, can you
So
repeat what's?
because so in this example, we can, so given only the ECC on the right, we can optimize the circuit on the left. So these 5 gates to the 1 gate
If
circuit.
you would like the first one to like swap the NMRs and then you just
Yes. So we don't need to store the 5 gate circuit to do the optimization.
One question. For an arbitrary size like 10, does there exist the ECC equivalence for circuits of size 10 that cannot be represented by smaller equivalents?
Sure. Yeah. So yeah, I'll discuss later. So
Sorry, is there any gates that require more than 2?
you mean 2 qubits more than?
Oh yeah, more than 2.
Oh yeah. So actually, so most compilers, including Quartz, so at the beginning they lower the 3 qubit operators into 2 qubit operators. So for example, CC naught, which is a 3 qubit operator, so it is lowered into 13 gates with only 1 qubit and 2 qubit gates.
So one more question. So let's say we have a bunch of gates, and I can either choose to first replace with this equivalent circuit class, or like I might have 2 choices of equivalent circuit class. That's possible. So does that order matter?
You mean when doing optimization?
No.
So yeah, so we use a search algorithm.
Okay.
Yeah, I'll discuss this later. Okay, so now let's look at some definitions. So yeah, so we want the EC set to be complete in that. So we define it to be NQ complete if it subsumes all transformations with no more than n gates and q qubits. And subsume means the transformation can be decomposed into smaller transformation in the EC set. So we can say that this EC set subsumes the transformation on the left. And yeah, yeah, let me introduce the overview of our system design. So I just noticed why the title is always good.
We can also move that bar.
and also like.
It's like the double
look at
three,
the-
like the triple dots.
the extra options you can hide there. Yeah, I don't-
No.
Okay, good. So first we input the gate set and N and Q, so for the NQ completeness. And we use an iterative approach to generate the circuits and verify equivalences to get the NQ complete EC set. Then we prune some redundancy in it and feed it into the circuit optimizer. And so after this part, so then it's more like a traditional optimizer that we take as input circuit and output and optimize circuit. So yeah, so how do we generate the EC set? So it's really, so for example, if now we have a J-1 Q is complete EC set. And at the beginning, J is 1, and we have an empty set as a 0 Q complete EC set because with no more than 0 gates, you don't have any transformations. And now we enumerate all possibilities to append a gate to the end of J-1 gate circuit. For example, if the circuit is like this, then we can put a hardware gate on QB0 or QB1 or QB2, or we can put some other gates, for example, a CNOT gate. These are two qubit gates, and it's asymmetric, so flipping it so creates another possible circuit.
Wait, are there infinitely many possibilities in this data?
The Q is a fixed number. So there are only 3 ways to the Hammer gate.
What if you put a U1?
Oh yeah, so we do it symbolically. So we
Oh,
just
okay,
put a
I see.
U1 theta here, or U1 theta 1 or U1 theta 2, so something. Okay, and yeah, we use a representative based generation algorithm which we call RepGen. So because there are too many gates to consider, so we want to consider fewer ones. So for each ECC, we maintain a representative. And for example, in the ECC1 on the left, we maintain the representative to be the empty circuit and not the 2 hallmark gates. And we only keep circuits with all sub-circuits being representatives. So what does this mean? So for example, in the middle, we can see that there are three gate circuits, which is HHX, XHH, and XHX. And notice that the 2 circuits above, they have a non-representative subcircuit, which is 2 H's. So what will happen if we have a non-representative subcircuit? Then we can actually replace it with a representative. So just an empty circuit. And we find that, oh, this is actually equivalent to the X, so the circuit with only an X gate. And because this is a smaller circuit, and so when generating for the we're generating 3 gate circuit, we already consider all gates with no more than 2 gates. So the X is already considered. So we already have all transformations. We already know which circuit are equivalent to the X, the circuit with only an X gate. So we don't need the 2 circuit above. And among the 3 ones, we only keep the XHX one. So yeah, in this way we can reduce the number of circuits we need to consider by 1 to 3 orders of magnitude. And then we use random testing to verify to prune most of the non-equivalent pairs. And for each pair of circuits that pass random testing, so in our verifier, we compute the symbolic matrix and use an SMT solver to verify it. So for example, if we want to verify that U1 theta 1, U1 theta 2 is equivalent to U1 theta 1 plus theta 2. This is equivalent to this SMT formula that for all parameters theta 1 and theta 2, these 2 matrices, the multiplication is equal to the matrix on the right. You can see that it is indeed equivalent. And then we iterate J from 1 to n to get an NQ completeness set. Okay, so after generating an NQ completeness set, we find that some other optimization can further reduce the number of transformations, but might interfere with the representative algorithm. So one is remove and use qubit and input parameters, because we kept generating circuits with exactly q qubits, but among the q qubits, there might be one of them that is not used. We can just remove it. So make the circuit optimizer, so make the optimizer slightly easier. And another is common subcircuit pruning. So if 2 equivalent circuits have a common gate at the beginning or at the end, we can remove one of the 2 circuits. So what does this mean? We can see that the 2 circuits at the bottom, they are equivalent. but they are equivalent just because 2 hallmark gates with a CNOT is equivalent to a flip CNOT with 2 hallmark gates. And the 3 gates on the above, they are useless. So and we can observe this because so they have a common gate. So there's a CNOT at Q0 and Q1 at the end. So if we find cases like this, then we know that so our ECC set, it already contains the two hallmark and the CNOT. This equals when it was generating the circuits of size equals to 3. So these 6 gate circuits, so they are just redundant. So we can prune this transformation, but we cannot remove both of them because in this ECC there can be other circuits, and we still want to have the equivalence between these two and others. So
wait, why would this case like even be here if like is like HHC0 is a subcircuit? And like either of the like representative is like the HHC0 or it's like the C0 HH. So why would this example even be? Wouldn't it get pruned there?
yes, actually I suspect so there's some previous when searching for a subcircuit we did it not very complete. Okay, so yeah, so now after that, so we feed the ECC set into the circuit optimizer. So for each ECC of site X, we can have 2 times X minus 1 transformation, which is the representative is equivalent to all other circuits. And we use cost-based backtracking search, which is adapted from Tazo, which is Zhihao's previous work. So yeah, so we maintain a priority queue sorted by cost, and we pick the candidate circuit which with the lowest cost in the queue, enumerate all possible transformations, and perform pattern matching. And so yeah, we just try to apply all possible transformations, and we ignore all candidate circuits whose call is greater than or equal to gamma times current bus, where gamma is a hypercurrency. So if gamma is equal to 1, then it's equivalent to a greedy algorithm. And in our evaluation, we set gamma equals to 1.0401. So
What makes this difference?
So this means it consider cost preserving transformation, but not cost increasing ones. So it allows transformation that don't change number of gates to happen. Yeah, so the search algorithm is there's a lot of space for improvement.
Like how many gates are like you working with? So like if the number of gates is smaller than like 10 to the 4th, then it's the same.
Yes, it's smaller than 10 to the 4th.
Like setting gamma to equal 1.001 is the same as like 1.001.
Yes, exactly. Okay, so in the end-to-end evaluation, we compare Quartz with 5 existing quantum circuit optimizers, and the matrix is a reduction on the number of gates. So the geometry mean of it on a benchmark of 26 circuits, and the dashes in this table means that either that circuit optimizer doesn't support this gate set, or it behaves very bad, and we think it's not necessary to run it. And we can see that we achieve on-par performance on the NAND gate set with the original NAND paper, and we outperform all other circuit optimizers in the 2 other gate sets.
How many ECC classes are you considering? For example, this kind of reference.
Yeah, so it's just here. So yeah, so the what we use is we use n equals 6 for the NAND gate set, and yeah, we can. So first we can see that the revision and the pruning techniques reduce the number of circuits in by a lot of magnitudes, and for NAND gate set with n equals 6, you can see that there are 54,000 circuits at the end. So they are divided into many EC sets, and about 90% of the EC sets, they only contain a pair of circuits, so just 2 circuits each. So it's still tens of thousands of ECCs in the EC set.
How many input Q?
Oh, yeah, the Q is always 3 in this table. So yeah. And so we also did some experiments. So for the NAND gate set, we tried different N and Q. So in the figure on the left, we tried N from N up to 7 and Q up to 4. And we use the search time out of 24 hours. So we can see that when Q equals 1, it does nothing, almost nothing. And when Q equals 2, it does something. And so when increasing the N gives no more improvement. And Q equals 3 is the best one in this here. And if we increase Q equals 4, then there are just too many transformation and optimizer chokes. So it's even 24 hours is not enough for the optimization. And you can see that we also did an experiment for Q equals 3. So on the different ends. So you can see on the figure on the right, so the x-axis is the search time from 0 to 24 hours. And the y-axis is the geometric mean reduction or the optimization performance. So when n is small, so that means the EC set is very small. The performance goes, so it improves very quickly at the beginning, and it goes flat up with the time. So when there's more time, and when n is larger, for example, n is 6, then it goes lower because the EC set is very large and it takes more time. But the final result becomes better because the larger EC set contains more circuit transformations, so it can do better. And yeah, so n equals 6 perform the best, and n equals 7 it just goes too slow even after 24 hours. And also know that there's a line called best. So that is, so among the 26 circuits, we pick the best EC sets for each circuit, and at that hour, and we compute the geometry, and we find that it is actually much better than any of them. So by about 1%. So in the best curve, so each data point corresponding to at that time, we pick the best n for each circuit. So for each circuit, we can pick a different n at that time, and we report the geometric mean of that.
But like after the second hour, it is different for all, and from 2 to 7.
Yeah, so actually we take a deeper look at different circuits. So we find that, so for smaller circuit, for example, this circuit have 58 gates. It's best optimized with n equals 6 and 7. And it's, yeah, so and it doesn't take any, it takes only very short time, and if you use a small EC set, you can never go as good as n equals 6 or 7. but on the right, so this circuit has 900 gates. And you can see that it's best to use NX24 or something. Because if you use a larger EC set, you can only do a few iterations even after 24 hours. So yeah, so this hint us that so we can actually, so there's a lot of space to improve the optimizer. So yeah, the simplest approach is that just to use larger EC set for smaller circuit and smaller EC set for larger circuit. But we believe that there's still a lot of more things to do to, for example, improve the search algorithm also. And there is another challenge that is optimizing on the physical layout. So we were focusing on the logical level of quantum circuit, but each quantum device has a different physical layout. For example, some 2-qubit operations, such as CNOT, can only be performed on specific pair of qubits, and the fidelity or error rates may differ when applying the same gate on different qubits. And there's a figure from another paper that shows an IBM quantum machine that so so each circle denotes a qubit, and only the edges can we perform CNOT. And the numbers are error rate, and you can see that. So for example, there are edges with 21 error rates, and there are edges only 3 or 4, so they differ a lot. So yeah, so optimizing and so mapping onto the physical layout is another challenge. Okay, so that's all of my presentation. So any more questions?
Can you try to tune the gamma for that, or try to allow for sort of temporal role in the circuit size?
So you mean the gamma here, right?
Yeah. For example, we control a upper limit and the circuit goes beyond that limit.
Oh yeah, actually, yeah, we did some experience with larger gamma for small circuit, and it did perform better. But for larger circuits, we find that we can never go into cost increasing transformation, or otherwise we will just choke and literally do almost nothing. So, and we wanted to be considered on this. We don't want to, because if so in the paper it seems that so if we use different gamma, it sounds like so that very hand-tuned, and we don't want to do that. So we just use gamma is equal to 1 plus epsilon for all circuits.
Was there any possibilities that you can split the whole? Because you know those circuits are calculated into one big pieces, and you can, for example, cut that into 3 pieces, and then optimize each one.
Oh yeah, that makes sense. But there's a problem. So in traditional programs, you can there are very clear function borders or file borders. So if you are compiling, for example, a large C++ program, but in quantum circuits, you just don't know where to cut. So yeah, because there's no clear separation, and yeah, so yeah.
Is it
What about just cutting according to depth?
Yeah, that could work, and
so there is possibilities, but
yeah, there's probably
there's no something like intrinsic barrier to do that.
right.
Wait, doesn't your definition of JQ complete, or like definition of how you construct the complete ECC set, that does preclude, like, for example, like this one. Like these two would never be in, like, what's the point of common subcircuit pruning? Because if they have a common subcircuit, they would have been like checked already.
Oh, actually, this is kind of implementation issue, because So when generating the circuit, we actually use a sequence representation here. So we are appending circuit to the end. So in this way, so when finding a sub-circuit, we are actually finding subsequences, which is kind of incomplete.
Oh, so it doesn't, I see, so it doesn't enumerate overall subcircuits, just like subcircuits that happen to be like substrings of the tree.
Yes,
Like that's why the two circuits on the next slide can actually be.
yes.
Like, is it possible that you can first like optimize the parameter n for each circuit and then run the optimizer, like your best plot?
Yeah, so I think so. If we are given, for example, 24 hours for optimizing a circuit, then we can spend first a few hours to find the best end. But if yeah, so but if the time limit is shorter, maybe we still want to generate the EC set beforehand and just use some of them.
So what does, for example, 30% circuit number reduction mean? Yeah, what does that mean by reducing, for example, 30% of the gates?
Oh, so this is on geometric average. So if the input circuit is 100 gates, on average you result in a 30 gate circuit.
Yeah, so what does it mean? So reduce the number of gates, and what does it give you in practical performance? Like reducing the error rate or the running time?
Oh, so yeah.
So you already mentioned that the number of gates is actually some kind of proxy to the actual performance.
Yeah, so given a quantum circuit, so if you are given a sequence of gates, you can put it in a circuit, and you will know the depth of the circuit. And usually the fewer the gates, the lower the depth of the circuit. And the depth is the running time, which will be smaller. And the fidelity is the multiplication of all gates in the circuit. So reducing the number of gates so it's almost always increase the fidelity of the result.
Yeah, it would be very nice to see some kind of number. That too.
Oh, but actually that won't make sense unless you have actually physical machine, because as you can see, the fidelity on each qubit, they are all different.
So there's no simulator.
There are, but we aren't compiling to the physical layout. So yeah.
But it would be still nice to see the number of depth reductions.
Yes, true.
Yeah.
So before optimization, there's a question of whether two given circuits are equivalent. What is the best heuristic or algorithm for that?
You mean our previous work, or?
No, just imagine you are given two quantum circuits, and the question is, are these two equivalent?
So do you mean like this equation?
Yes, for example, you provided ECCs of size 2 or 3, reversing the Hadamard.
Sorry, I didn't get it.
For example, 2 Hadamards are equivalent to
Nothing.
nothing.
Yeah.
Imagine you are given 2 circuits of size 100.
Okay.
Are they equivalent?
So yeah, so you can actually do the matrix multiplication if there are not too many qubits. So yeah, so for example, if there are 5 qubits in total, and each circuit containing 100 gates, you can just do the 2^5 by 2^5 matrix multiplication for both of them, and then these equations and verify.
So the random testing is basically you put, for example, there's a parameter theta, and you just put some random number on its times.
Yes,
And
exactly.
finally, you use the symbolic.
So random testing is we assign random value for all parameters, and we also assign random vector to actually make the matrix to there's to make the matrix, so multiply a vector, a column vector at the end, a row vector at the beginning to make it only one number.
Okay, that's a very common.
Yes.
Yes. If there's no other question, let's thank Mingkuan again.